In the next subsection, I want to show you how to overcome these weaknesses of inverted indices, that not all texts where we might want to search have these word boundaries. And so we want to have something more flexible. In a sense, we want a full text search, a full text index. Before we get back to the text indexing problem, though, I want to stress how remarkable suffix trees are. And so this is a tiny bit of a history lesson as well. And I want to illustrate it on this problem, the longest common substring problem. It's a problem where you're given a set of strings, S1 up to Sk, and you're trying to find the longest substring that occurs in all of those k strings. So again, substring, not subsequence, so it must be some contiguous range. And you want to find this part of the word in all of the strings that you're given. Here's a tiny example with just 2 strings, and it's already not completely obvious at first sight. What's the longest substring they have in common? Can someone find it? Pardon? Life? Alive? So it's tricky because humans tend to recognize the parts. Well, the first is a sentence, and so we're a phrase. And you have to combine things. But yeah, alive is the longest thing they share, just because the second, there's not much left to make it longer. Now, suppose you have 100 of strings. It's not clear how to do this. And in particular, it's not clear if you can do it in essentially the same time you need to just read all these strings once. But it's possible. At least in big O of. So you're allowed to read the strings a constant number of times, conceptually. But then you're supposed to tell me. And it's remarkable that this might be possible because it seems you have to... What would be a simple approach to solve the problem? You could try to go through all possible substrings of the shortest string and try to search them in all the other strings. But that's even that is quadratic in the length of the shortest string, and you haven't even searched the others. So you would need to use some string matching method for the other strings, and this would be way slower than just reading all the strings once. In the worst case, they're all the same length, all fairly long. So not so clear how to do it. But yeah, suffix trees will allow you to do this in that time, and we'll get there. It's not even that complicated. It's just building on a few really cool abstractions. To further highlight why this is even surprising for experts, so this is a quote from Dan Gusfield's book, which might be called the Bible on suffix trees. Is the most complete collection of things you can do with suffix trees. And he says, he quotes Donald Knuth, which you may know as the inventor of LaTeX, not LaTeX, but TeX, this typesetting system, and also the art of computer programming. And it's fair to say that he's a founding father of computer science, or theoretical computer science, and also a genius in definitely several ways. But definitely a smart person. But in 1970, he said that he conjectures there's no linear time algorithm, with this running time for this problem, finding the longest common substring of a set of strings. And it was only 3 to 4 years later that he was disproved, that he was proven incorrect by the introduction of the suffix trees. But he didn't foresee that, and he didn't see how to do it with a suffix tree. So it's the same Knuth from the KMP algorithm. All right, I hope you're hungry for what's coming now. I tried my best to motivate this. So what is a suffix tree? The definition is just this little box, and it's all built on things you already know. The suffix tree for a text is the compact trie, so that was the version without the unary nodes, of all the suffixes of this text. So a suffix is a substring that ends at the last character. Now, for convenience, we'll always add this end of word character to our strings. So our text will have n characters, but actually the n index, the n plus first character, is always set to the $. So we will always assume this here. And then we can build this try over all the suffixes because they're then prefix free. And yeah, that's pretty much it. And so maybe let's spend a minute on a small example. Suppose our text is this, banana. Then these are the indices. So I take all the suffixes and insert them into a try. The easiest way to build a compact try, if you have to manually do it, is to first build the standard try and then compactify things. You can also do it directly, but for the manual execution of this algorithm, let's maybe not torture us too much. So we first insert banana. So we start at the root. Then we do B, A, N, banana, and the $, and then, well, I feel I don't repeat the string. So instead, I just say the starting index of that suffix. That's a little more space efficient too. I don't have to repeat the suffix all the time because it's always the suffix of the same text. So I'll instead just store the text once, and the leaf says start at 0, and you will get the string that ends here. So that was the first one. How about starting at one character later? That's the lovely anana. So I branch out at the root with a different letter. And that brings me to the leaf with a 1, because it started at position 1. Nana is the next one. So let's take this down here. Two. And now it gets more shorter and shorter, so it gets a little faster. Anna is already in here. I just have to add a new leaf. And that starts at 3. 4 is na. So I'm here and add a new leaf. 5 is just an A. So again, we branch out to a new leaf. And well, we could also include just the $. And so that's the standard try. Now we want to compactify this, which means remove all the unary chains. And while we're at it, we can try to make it a little nicer. No, that's already leaf. Then here we have $, and NA. Oh, come on. Now in the compact try, I should write the position that we check next. So if we want to do this correctly, this should be 0. This is a 1. This is a 1 as well. And this is a 1. So far we haven't skipped anything. But then here this NA becomes 1 where we skip. This goes to 5. Okay, another 2, 3. And NA $, just goes to this straight away. This one is just one long branch, so this is actually not a 1, but leads immediately to this leaf. And on this side, we have, sorry, this n, this is also not a 1. It's a 2. And then $2 and an n brings us to the 2. So they get quite a bit compacter. I tried to do this in detail for this one so that you also see the tri-compactification another time. I don't know how valuable it is to follow this on the slide, but if you draw the same thing a little nicer and sideways so that we can read the strings better, that's the same. Now, I will usually write on the slides the full label of the edges as they would be filled if you go to the leaf and then check, just because it's, for us, easier to work with. But what's really stored is, of course, this one, where you have only the first character each, and the internal notes tell you what's the next character to compare. Okay, so again, the three things. This is what you often want to write on paper so that you can work with it as a human. It has the explicit strings in the leaves, and it has the full labels on the edges. We don't really store the strings in the leaves. We store just the starting index, as I showed you in the example. And we also don't really store these edge labels. Instead, we just store the first character. Okay? Now, I've shown you on this example how you can construct a suffix tree. Let's see how long this takes if we follow this algorithm. We have a text with n characters, so it has n+1 suffixes because I added this $sign. And if I insert a string into a trie, that essentially takes as long as the string is. So if I insert n things and they're n long, so at least the longer half, or at least n half long, so you get this quadratic divided by 4 at least. It takes theta of n squared time to construct the suffix tree using this method I've just shown you. Insert each suffix one after the other. Now that's really crappy, because in quadratic time you can do a lot on strings, and in particular you can't solve this problem with longest common substrings in linear time if it already takes you quadratic time to build this suffix tree. So there's clearly something missing. The definition of the suffix tree is quite natural and easy to come up with, but the real achievement from that time is that you can construct the suffix tree in linear time. Instead of this quadratic, you can bring it down to theta n, which is, again, roughly the same as reading the text just once. In that same time, you can build this compactified version of the trie, and we'll eventually see how to get there, but it will take us a few more steps in between before we can conclude that part. For now, we'll just take this as a magic black box. You can build the suffix tree in linear time. It's a little complicated, but once you have it written up, you can just reuse it many times. It's a little tricky to understand, but we'll get there. It was a theoretical breakthrough because it allowed to solve this problem. I'll show you the details in this time that Don Knuth conjectured is not possible. And the construction can be done quite efficiently in practice. So a version of this is still in use in applications like finding matches of your RNA snippets from a PCR test in the genome database. So for now, I want to take this for granted and see what can we do with it. That will be the first step as a motivation, why you want to learn, why you want to see the details of how to construct them in linear time. Before I leave you for the break, one last longish question that I maybe just leave open for the break. So let's have a look at the Slido question. There's quite a few different answers, and you see all of them got some votes. And here's the ones that deserve to have votes. Most of you did fine. So this last part is what I just mentioned. We just treat it as a black box for now, but we'll get there. So let me briefly comment on each of these. The first one, I said, is just for convenience to represent the tries. So we do require the text to end with a dollar, or actually we just put the dollar there. The size of the suffix tree is linear in the text size because it stores a linear number of suffixes, n suffixes. And so this quadratic size was for simple tries, but for compact tries, it's linear in the number of nodes is linear in the number of strings, right? And that's n. T is not a standard trie, it is a compact trie of all the suffixes. The leaves don't really need to store a copy, so they shouldn't because it's waste of space. Instead, they store just the starting index. We can naively construct suffix trees, and then it takes quadratic time. Yeah, potentially with a compact trie constructed right away, you don't always need quadratic time, but definitely in the worst case you do. But yeah, the big magic step is you can do it in linear time. Worst case, I haven't told you how yet. And the last one is a kind of a mini. It doesn't have n leaves as n+1 because it has n+1 suffixes once you add the dollar. Oh, right. That one's not too important. We don't really need the dollar leaf for any interesting applications, but following the definitions, that's what's there.